This will be mini lecture 18. This is, we're going to really start moving into the second main component of Engineering 17, what sometimes in some courses they call the transient analysis portion of the course. A little bit of introduction via where we've been. If we set aside the introductory lecture on operational amplifiers, we pretty much spent over a month basically learning mesh and nodal, including calculating power. Then we also talk about Thevenin and Norton circuit. But largely the essence of your last month plus was essentially to learn or to have some proficiency in developing a mesh or nodal analysis procedure. We did this with sources and resistors. And these sample circuits, what essentially we did, we developed n equations for n unknown, 3 equations for 3 unknown, 4 equations for 4 unknown, and the unknowns being the node voltages or the mesh currents. And you could put these equation coefficients into a matrix and solve them using your calculator, or probably some sites on the web. I provided you one. So it's a way to learn mesh and nodal with simple DC circuits, simple resistive circuits. Today we start really changing course here slowly. So this lecture will be an introduction lecture. We're going to introduce 2 new elements, and they are fairly significant elements. Okay, so let me share screen and then we'll start talking about them. These are the 2 elements that we're going to spend this mini lecture discussing here. We're going to introduce the inductor, and then we're going to introduce a little bit later the capacitor. So this lecture is really an introductory lecture. The examples that I will be doing in this lecture are not examples I'm going to ask you to do. They're going to mostly be illustrative example about how these elements work. Okay, so the first thing that comes to my mind when I look at these elements, you need to think these 2 elements are passive elements. Okay, they are passive elements. Resistor is the other passive element. So in this course, we're going to see 3 types of passive elements. The resistor, which we spend the first month plus working with. And now we're introducing 2 new elements, the inductor and the capacitor. The main difference between these elements and the resistors, they are called energy storage elements. Energy storage elements, which is going to make them very, very much useful from an electrical circuit standpoint. They are able to store energy in some particular time and release later. Okay, so we're going to spend, because this lecture is the introduction lecture, and then we're going to put them in circuits and analyze them. All right, so today I'm going to be doing a little bit of a physics review, if you will, in terms of what these elements are, how they're constructed, because how they're constructed has a lot to do with their voltage current relationship. This is not a micro course. This is a course where we assume a particular property for elements and we put them in circuit, and your job is to analyze the circuit. When I mean analyze, find current, voltage for circuits once we have the elements and the elements defined, and typically that means the voltage current relationship. So for each of those elements, we're going to spend time defining the voltage current relationship for the inductor and that for the capacitor. And then we're going to also cover power, just like we did for the resistor. The new thing, we're also going to cover energy, because these circuit elements, these new elements, they can store energy. Okay, so these are going to be essentially an introduction on that. We're going to do it for the inductor and for the capacitor, and we conclude this lecture by doing something that has really modest application in this course and in real life, how to combine these elements in series or in parallel. We need that for completion so that we know how to do this, but rarely you'll be doing this in this course, basically. Okay, so this is where we are here. Energy storage element, so far we've been dealing in terms of, again, I first start by saying inductors and capacitors are passive elements. That is fundamental to know this. okay? They are passive elements, all right? And later on, I'm going to say to you, once we have the voltage-current relationship, they need to follow the passive sign convention, okay? So resistors that we've been working with, that's the only passive elements we had besides sources. Resistors do only one thing. They burn power, they burn energy, okay? They dissipate power and energy, all right? So whereas if you look at sources typically produce energy and power. Capacitors and inductors are different passive elements. They can store energy at some point in time and release it later. They actually don't dissipate anything. In the ideal case, an ideal inductor, an ideal capacitor, basically don't dissipate any power, don't dissipate any energy. They're stored and released. And that's going to be an interesting thing to think about these elements in that way. They, again, follow the passive sign convention. Okay, so we're going to start with the inductor. I'm going to bring you back to your physics, electricity, and magnetism class, how these elements are constructed, because the way they are constructed essentially has to do with their voltage-current relationship as well. We are not going to use that, though, in this course. In this course, we are going to assume the element, and then we're going to solve using mesh and nodal. All right, so let's begin with the inductor. If you remember your physics instructor, current that flows through a wire produces a magnetic field, and you can tell your physics instructor was doing the right-hand rule to show you the orientation of the field, basically around the current that's flowing up, and then your right-hand rule tell you the direction of the magnetic field, right? What we do in terms of creating an inductor, we essentially make the wire into a coil. We essentially wrap it generally around a particular material. We make it into a coil to strengthen the magnetic field that's inside the center of that coil. That's what that H here. So we make it into a coil, okay? And we create an inductor. An inductor stores energy in its magnetic field. Often the wrapping of the coil is around a particular material to focus the energy and to avoid leakage, okay? And you can see what I'm starting to do here. I'm starting to essentially show you the passive sign convention. You got an inductor, so that's going to be somewhat the symbol for the inductor. And then it has a voltage and a current that satisfy the passive sign convention. So more specifically in my little house here, that's my as creative as it gets here. This is the symbol for the inductor, that coil. Again, the inductor has an inductance L. L depends on the number of turns, the material that it's wrapped around. It's a physical, just like the resistor, it's a given. So the inductance in Henry is given. Okay, it's not something you need to figure out. This is a characteristic. If you buy an inductor, it comes with an inductance. All right, so it is given, and it generally depends on the number of turns, generally depends on the material that the turns are wrapped around, okay, to create that, essentially that inductance. This obviously is a super important formula. It tells you the relationship between voltage and current following the passive sign convention. When the current is entering, again, I'm going to underline, when the current is entering the positive terminal of the voltage, then the voltage is equal to the inductance, which is a physical characteristic of the inductor, times the time derivative of the current. Okay, so therein lie why, where we're going to go over the next 3 weeks plus in this course. Okay, so this particular elements, the inductor and the capacitor, they are going to bring your differential equation course, specifically your first and second order differential equations, into circuit analysis. This is why I spend so much time getting you to be proficient in mesh and nodal with resistors, because from this point over the next 3 weeks, we are going to be essentially injecting first order differential equation and then later on second order differential equation into mesh and nodal. And I'm going to carefully work with you to develop that skill set. So, and the reason we have that, that's because for an inductor, the voltage is related to the current by its derivative, time derivative. Okay, so V, and you can see what I'm starting to do here. I'm starting to do V as a function of time, because we're slowly going to have things that changes, is equal to the inductance times the derivative of the current as a function of time. All right. All right. The next lecture, I'm going to put them in circuit. Now, these circuits are going to be simple circuits. They're going to be circuits with DC sources, constant sources, but they're going to have switch that are switching them on or off. Okay. So this is an important slide. This relationship for the inductor, you cannot swap it. I never want to see I is equal L dV dt. Okay, the voltage is equal to the time derivative of the current. Let me tell you why this is very important to do that. What happens when everything is constant? When everything is constant, the derivative of the current is zero. Okay, so the voltage is zero. All right, which makes sense if you look at how the inductor is constructed. The inductor is essentially a wire that wraps around as a coil. So clearly, if there is no change, essentially in time, it behaves like it's just a wire. So this particular relationship follows from how the inductor is constructed, being just a wire that's wrapped around in the manner of a coil to create a high magnetic field. So voltage is proportional to the derivative of the current, the time derivative of the current, and that constant of proportionality is the inductance. So, okay, let's make sure we know this, because that's fundamental to the inductor. So if, for example, and so I'm going to run to a few examples in this lecture. They are not examples you're going to be asked to do. Okay, they are examples that I'm hoping that illustrate basically how these elements behave or work. Okay, so in this particular case here, if I put an inductor and I connect it to a 1 amp current source, a 1 amp, that's a constant current source. Basically, you can see that the voltage is 3 Henry times the derivative of 1 amp. The 1 amp is not changing, so the voltage is zero. Okay, it's to say an inductor excited with constant sources behave like a wire, behave like a short circuit. Okay, so, and that flows from the construction of the inductor, because the inductor is wires made into a coil. All right, so when things are not changing in time, it behaves like a wire. Okay, so if we look at this, looks like a complicated example, but because the source here is a 2-volt source and it's been 2-volt forever, this is a circuit potentially has been 2-volt forever, all the inductors here behave like a wire. So we can look at this circuit as this. Okay, this is just again illustration of the inductor's behavior when it is faced with a constant source and nothing has changed. Okay, so again, just a little bit of a back end. Just this is the most important slide thus far. The inductor relationship, the voltage current relationship for the inductor. The voltage is proportional to the time derivative of the current, and that constant of proportionality is the inductance in Henry. The inductor follows the passive sign convention, and the symbol is what's shown in that little blue house here. Okay, so that's the inductor. So we covered the voltage current. I'm going to also cover power and energy shortly. Okay, and that's going to be what we do for the capacitor and for the, after that. Okay, so if we know, we said the voltage is proportional to the derivative of the current, so the current is the antiderivative, it's the integral. We are not going to use this ever in this class, okay? The derivative relationship is what we're going to use, not this, all right? But so we'll be complete so that if you did have the voltage, you could actually integrate the voltage and get the current that flows from that. And we can assume the constant of integration K. We can assume it's zero because at some point the current should be zero on the inductor. Okay, but we won't be using what's boxed here is really what we're going to be using anytime we have an inductor. Okay. All right. So power. We're going to go power, and also we're going to go energy. We didn't have to go much energy on resistors because a resistor essentially doesn't store anything. It just burns power. So for inductors, again, you can see that I'm putting power as a function of time. This is what we call instantaneous power. Power at a time t. It is the voltage at time t multiplied by the current at time t. Again, when the passive sign convention is followed, I can actually replace the voltage by its relationship to the current. So if I do that, you can see that I can write the power entirely in terms of current. It is L di dt times the current I, and power is in watts. Power is going to fluctuate with time. Okay, so what essentially makes these elements important and really, really useful in electrical engineering is that they can store power. They can store energy and release energy. Okay, so I'm going to use an analogy in this class. I'm going to probably overuse it, and I'll ask you to forgive me when I do overuse it, but I think it's an excellent analogy. The way I want you to think about an inductor and later on a capacitor, because it's the same concept, I want you to think about an inductor as your gas tank. Okay? Your gas tank, think about your gas tank as an inductor. And think about the level of gas as the energy, the level of gas in the tank as the energy in the inductor. So let's cover energy, and then we will see that, because what we're going to see essentially here is that the inductor power, this is really new. This is really new, very new. The inductor power can be negative. Okay? It can be negative when it's releasing energy. In other words, when it's giving off energy, it's going to give you the impression it's behaving like a source, but it's not. It's a passive element. And it can be positive when it's storing energy. So the inductor takes on energy at some point, release it later. So the power will tell you when it's taking on energy and then when it's releasing energy. That's the analogy with the car gas tank. And let's cover energy and I'll come back to that. Okay. So if you think about power and the relationship between power and energy in terms of your physics class, power is a derivative of energy. Energy is the integral of power. Okay, so they are related. All right, so in many respects here, so if you think about power being the slope of energy, so when power, which is the slope of energy, when power is negative, the energy is dropping. So the content energy is being released. If, on the other hand, power is positive, energy is increasing, because that's the slope. Energy is increasing, it's storing energy. Okay, we'll come back to that. So again, power is really the energy per second. So it is really the derivative of energy. And to find the energy stored in the inductor between some time t, between two time period t naught and t, we simply integrate. We simply integrate over that duration. So we integrate power to find energy. Again, remember I told you that power is a derivative of energy. So energy is the integral of power. You do not need to know this, this proof that I'm showing you here. You need to know this. The energy in an inductor at any time t is 1/2 times the inductance times the current squared. The energy is always positive, always. The energy is always positive. So I'm going to now have that conversation using the analogy, the gas tank analogy. So we've actually covered, for the inductor, we cover the voltage current relationship, we cover power, and then we cover energy. Okay, so here is how I want you to think about this. Remember the gas tank analogy that I mentioned? How much gas is in your tank is the energy in the inductor. So you have some gas in your tank. So you go into the gas tank and you fill up, you're adding gas, you're filling up. So what's happening to the gas tank? The gas tank is increasing, right? Because you're filling up. So your gas tank is storing energy, all right? So in terms of power, power is positive because the level of energy is increasing in your gas tank. Power is positive. And then you stop putting gas in your car. You put essentially the nozzle back, and then you start driving your car. So as you drive your car, the amount of gas you have in your gas tank is going to slightly dropping, right? As the gas is dropping, the energy is getting less. So the slope of the energy is negative. That's the power. As the energy drops, the slope of the energy is dropping. your gas tank doesn't manufacture gas. It doesn't manufacture energy. All your gas tank does is take on gas and then give it back later when you run your car. So it's a perfect analogy for an inductor, and that's what the inductor does. The inductor can be taking on energy in some point and release later. Okay, we're going to need to talk about this a lot over the next few weeks, but for purpose of this here, this is a super important formula. The energy in the inductor is 1/2 times the inductance times the current squared, and it is always positive. Okay. Later on, we're going to talk about initial condition, and we're going to link it to that energy in terms of the initial condition for differential equation, which comes from your differential equation class. All right. So another example, again, you are not going to be solving example like this. I'm not going to give you functions, current functions that have triangular shape. This is just to show you, give you somewhat of an illustration how this thing works. Let's potentially say I put this function in the current so you can see what I mean. So what we're going to do, we're going to have current and voltage sources that are constant, but we're going to have switches that switch them on and off. Okay. But for this example here, I have this triangular pulse. So the current is 0 up to time t equals 0. And between 0 and 1 second, it is t. And between 1 and 2 seconds, it is 2 minus t. So it's a triangular pulse. And then we're asking to find the energy stored in the inductor and the energy dissipated in the circuit, basically. So you can kind of tell that the resistor is going to dissipate all the energy eventually. Okay. So the inductor is going to store energy at some point, release later, but the resistor doesn't do anything too sophisticated. It just burns it. All right. So we have the current here. I could easily calculate the power for my resistor, Ri squared, and so forth. So let's see how we do this. So here is the energy stored in the inductor, 1/2 times the inductance times the current squared. Okay. So, and I plot the current, I plot the energy for you using the 1/2 times the inductance times the current squared. So for between 0 and 1 is 2t squared. And between 1 and 2 is 2 times 2 minus t squared. Okay. So you can easily see in the energy in that case how it is charging. It is charging between 0 and 1 second. It goes from 0 joules to 2. And then between 1 and 2, it actually discharges between 1 and 2. Okay. So it's a good illustration. Again, you're not going to be solving problem like this, but I think it's a good illustration on how the inductor store and release energy in a particular circuit. So if I then look at the power, again, I can look at the power in the inductor by essentially calculating this right here. All right. The current times L di dt. I can clearly see when the energy is increasing, the power is positive. And when the energy is decreasing, the power is negative because power is the slope of energy. So you can see when it is storing energy, power is positive. When it is releasing energy, power is negative. So it's a very elegant way to look at the role of the inductor. Again, I encourage you to think of the gas tank. The amount of gas is the energy in the inductor. As you fill up, the amount of gas gets up. So the power is positive because power is the slope of energy. And as you're driving your car, the gas content is going to get less and less and less. Power is going to be negative, and the energy is essentially dropping. Okay. So if we look at the energy that the resistor puts out, the resistor dissipates, we can integrate power across the resistor, and we can show that it's 2/3 joules. All right. Okay, again, this is an illustration of what inductors can do, not the type of problem you'll be solving. All right, so let's introduce the capacitor in a similar way. So before I go introduce the capacitor, again, I'm going to tell you that the next lecture, we're going to put these things into circuits, and we're going to start going back mesh and nodal with these elements and bringing in your first order differential equations. That's what's coming over the next 2 lectures after this. So the capacitor is a it's constructed totally differently. If you think about the inductor as wire that we make into loops to essentially reinforce the magnetic field inside the loop, a capacitor ideally, essentially, we bring two plates in proximity. We bring two plates in proximity, typically separated by a so-called dielectric, which is an isolant, something that doesn't let electricity go, electrons go through it, okay? So we basically bring two plates in proximity separated by a distance, a d. Of course, there are many, many more sophisticated ways to create capacitors today, but this is essentially a basic capacitor. And for this particular structure here, the capacitance is the permittivity of the dielectric times the area of one plate divided by the separation of the plates. Things you've seen in physics. Again, we're not going to do these kind of things in this course, but how the capacitor is constructed is important. So why it's important? Because it's essentially separated by an isolant, okay? And you're going to see when we write the capacitor voltage current relationship. So in the bottom right, I'm showing you the symbol for the capacitor as the parallel plates here. The first thing I want you to notice here is the capacitor follows the passive sign convention. Both inductors and capacitors are passive elements. They follow the current enters the positive terminal. So we affectionately say voltage current relationship. For the capacitor, it's current voltage relationship. For the capacitor, the current is proportional to the time derivative of the voltage. And that constant of proportionality is the capacitance in farads. Okay, so I for a capacitor is C dV dt. And obviously the capacitance is essentially a given spec for how the capacitor is constructed. So you can see that the inductor has a totally different current voltage relationship than the capacitor. For the inductor, the voltage is proportional to the derivative of the current. For the capacitor, it's the current proportional to the derivative of the voltage. Why this is important? What happened if you put a capacitor and you put it across a constant voltage source? The derivative of the voltage is going to be zero. The current is going to be zero. That makes sense based on how the capacitor is constructed. It's two plates that don't touch. So if you put them in a circuit that everything is constant, it's essentially look like an open circuit. Okay, that makes sense the way it is constructed. That's what I'm saying. The voltage current relationship, or in this case, the current voltage relationship for the capacitor, it's really based on the way the capacitor is constructed. Okay, the current is proportional to the derivative, the time derivative of the voltage, and that constant of proportionality is the capacitance in farad. All right, and I'm showing you the electric symbol we'll be using for the capacitor, following the passive sign convention. So again, I'm showing you some basic examples. This is an example you could do now that you know how to do op amps, ideal op amps, but this is not really the time for this yet. So this example is an interesting example. You'll see why. Find the output voltage V0 of the circuit, with this being an ideal op amp. Okay. So if you remember ideal op amp, essentially the op amp draws no current. The two terminals here are about the same voltage. No KCL at the output of an ideal op amp. So we're going to do KCL right here. Okay. So let's set up things. I put current on my capacitor and my inductor. I'm sorry, on my capacitor and my resistor. And then obviously the KCL at node V1, and V1 is 0 because these two things are at about the same value. That's one of the ideal op amp rule. So IC is equal to IR. And then I can write IC using the capacitor relationship. Is a derivative of the voltage across the capacitor, which is V minus 0 because V1 is 0. And of course, the resistor current IR is V1 minus V0 divided by 1, which is minus V0. So I put these two things in the KCL and we get this, okay? The output of this circuit is a derivative of the input. Actually quite cool to have that, okay? Quite cool. So you can see how very simply you can make really more sophisticated circuits than what we were able to do with just a basic resistor. In this particular case, we can essentially create a simple circuit that gives you the derivative of a function using an op amp. Okay, so these are good examples. Here, let's see. I think pretty much what I'm going to do now is show you how to combine them in series and parallel. And the next lecture is probably one of the most important lecture of this entire set of lectures, because we're going to start dealing with how do we do mesh and nodal with circuits that now has either one inductor or one capacitor. Okay, so before we start combining them, let's cover power and energy, just like we did for the inductor. So for the capacitor, the instantaneous power again is voltage times voltage as a function of time times current, except in this case here, you can express the entire power in terms of voltage. So what I'm hoping you get to see now is that for the inductor, the current through the inductor is the important parameter. For the capacitor, the voltage is the important parameter. Okay, so this is the instantaneous power. And remember my analogy with the gas tank. As the gas is increasing, you have more energy, so power is positive. As the gas is dropping when you're driving the car, power is going to be negative because the energy is dropping. So power is negative when it's releasing energy, and power is positive when it is storing energy. Okay, so and then if we go ahead and calculate energy by integrating power, again, you don't need to show me this proof that I'm showing you, but you need to know what's in the box here. The energy stored in a capacitor at any given time t is 1/2 times the capacitance times the voltage squared. Okay, the energy, which is the amount of gas in your gas tank, it's always positive. You can't have negative gas. You can have zero gas, but you can't have negative gas. You either have gas or you have no gas. So the energy is the amount of gas in your gas tank. Okay, both for the inductor and the capacitor. For the capacitor, it's 1/2 times C times V squared. It's always positive. Okay, so these are important things that let me just quickly go to the document camera here and just put some kind of recap before we go ahead and go ahead and essentially learn how to combine them in series and in parallel, which is of modest value. Okay, so and hopefully it will. So what we talked about here today, we talk about the inductor. Okay, an inductor of inductance L, and we also talk about a capacitor of a capacitance C. The first thing we talk about here is this is a voltage. It is a passive element. Okay, so here we put a voltage here, and the current is going into the positive terminal of the voltage. These are both passive elements, which means follow the passive sign convention. Okay, so that's the first thing. And then, of course, for the inductor, one of the most important formula is essentially the voltage. Again, we're going to start getting used to putting voltage as a function of time is equal to the inductance times the derivative of the current as a function of time dt. Okay, okay. This is assuming, again, that the passive sign convention is followed. For the capacitor, sorry, I forgot to put my current here. For the capacitor, it's the current as a function of time, which is equal to the capacitance that the derivative of the voltage as a function of time dt. These are super important relationships. You cannot deal with inductors or capacitors without knowing this. Okay. And then we talked about power as a function of time, which is V of t times I of t. And if we do that, essentially, what do we have here? We have L di of t dt times I of t. Okay. And for the capacitor, power again is V of t times I of t. So what is that? It's V of t times C dV of t dt. Okay, so that's power for the inductor, and that's power for the capacitor. These are important, but very important is, and I'm going to say, I put W sub L to essentially show you the energy in the inductor. It's 1/2 times the inductance times the current squared as a function of time. This is really important. And for the capacitor, the energy W sub C, to indicate for the capacitor, is 1/2 times the capacitance times the voltage squared as a function of time. So what you're seeing essentially for the inductor, the current is the important parameter, because the energy and the power depends on the current. For the capacitor, it is the voltage. Later on, and again, my document camera crashes here. So just so that we know here, for the capacitor, the important parameter is the voltage, because you can see that I can express the power and the important energy, how much energy is in the capacitor in terms of voltage. And you notice that the energy is always positive. Energy is always positive. It is the gas in your gas tank. And later on, we're going to link the energy in the inductor and the energy in the capacitor in. We're going to link it to initial condition as when we solve these circuits. So we're going to link the energy. We're going to link the energy in the inductor and the energy in the capacitor to initial condition, as when we put these elements into the circuit, we're going to be solving differential equations pretty shortly. During the next lecture, we begin this process in the next lecture. So let me go back to the PowerPoint. So finally, we're going to finish this particular lecture here in talking about how do we combine them in series and in parallel. This is a very, very, very modest value. Okay, but we need to do this for completion. We need to do this so that you at least know this. The way I tell students to remember this, inductors follow the same rule. They're not resistors. They follow the same rule as resistors in terms of how we combine them. In other words, if we have a bunch of resistors in series, of course, by now you know what it means when we have something in series. We're really talking about something that, we're talking about inductors that have the same current. That current I cannot go anywhere but on L1, L2, L3, and so forth. So series mean you have the same current. Then you can combine them into an equivalent inductance by just simply adding the resistance. Inductors follow the same rule as resistors. They are not resistors. We've just been explaining that over the last half hour. They store and release energy. They don't dissipate anything. Okay. So if we put them in parallel, again, you can use the parallel formula for the combination of resistors to essentially get an equivalent inductance if you put them in parallel. Very, very rarely we're going to be doing this. Okay. But, we need to know this because it's just for completion. Parallel follow the exact opposite. So parallel, essentially, when they're in series, you use the parallel formula for resistors, okay, to get an equivalent capacitance when they're in series. And if they are in parallel, we essentially add them. We use the series, so they follow exactly the opposite rule of combination of resistors. We add them in when they're in parallel. Just add the capacitance to get an equivalent capacitance. Okay, so that's where we are. So let me just going to give you what's coming onto the next mini lecture. Let me just stop sharing here. So what we do in the next mini lecture, we're going to essentially have circuits that have constant sources with a switch. Okay. And that's what we're going to be doing over the next three weeks plus. We're going to have constant sources, but we're going to have, they are switching on and off. Okay. Disconnect and connect. And then we're going to have the first group of circuits we're going to see. We're going to have circuits that have either one inductor or one capacitor in the circuit. That's going to basically bring the first order differential equation into our mesh and nodal analysis. So we're going to learn how to develop a mesh and nodal to come up with a differential equation and learn to solve that. I'm going to show you, I'm going to send you an announcement that gives you a little bit of a review of your math, of your differential equation course, wherever you've taken it. If it's Sac State, it's Math 45. Okay. But that's what we're going to be doing in the next mini lecture. We're going to look at circuits that have either one resistor or one inductor. We're going to call them first order circuit. That is a circuit that has one energy storage element, either one inductor or one capacitor. I'm sorry, one inductor or one capacitor. They can have any number of resistors and any number of sources. Okay, so that's what's coming our way. This will be, just getting us ready to do that, particularly when we look at the page that I showed you on my document camera here. What's the voltage current relationship? What's the power? And what's the energy for these elements? Thank you.